and I'm here to talk about the salts of the Earth and how they could help when looking for life in the solar system. Earth can provide us with analogs that can mimic exoplanetary environments, and one of the ones most often used for Mars is the Atacama Desert. I'm really proud of this graphic. So in the Atacama, life has been shown to live off the deliquescence of salts, but can the salts that I studied deliquesce in Atacama conditions? So for my project, I tried to answer two scientific questions. Could nitrate salts or their salt mixtures uptake or release water under Atacama environmental conditions? And could the temperature and relative humidity values lead to nitrate salt deliquescence? So to answer this, we used a Raman microscope attached to an environmental cell in which the temperature and relative humidity could be controlled, and we used this to study the phase transitions of our salts of interest. So we can answer our first question. Could nitrate salts or salt mixtures take up water under Atacama conditions? Well, yes, and thank you for coming to my talk. But let me tell you why. And so the first thing that we're going to do is look at the spectral series of the pure magnesium nitrate. So if we look at the crystalline nitrate, which is going to be shown by the black spectra at the bottom, it starts off at a higher wave number of 1062, and as we decrease the temperature and increase the relative humidity, it's going to stay there until it reaches the deliquescence relative humidity of 63%. At which point it shifts to lower wave number of 1052. So it's going to stay here, and this is really cool. It's going to stay here. And as we increase the temperature and decrease the relative humidity, it stays at that lower wave number until the efflorescence relative humidity of 23%. And that means that magnesium nitrate, the pure one, can maintain a metal-stable brine for over a 40% RH change range. So we repeated these experiments multiple times over different temperatures, and we made this lovely phase diagram. And it's as temperature versus relative humidity. So for the pure magnesium nitrate hexahydrate, the deliquescence is going to be shown by the blue dots, and the efflorescence is shown by the orange squares. And it was relatively temperature independent and occurred around 25% RH. So magnesium nitrate exhibited a very large hysteresis, which you can tell by the gap between the deliquescence and the efflorescence relative humidity. And this is going to be our metastable brine region. But I also mentioned salt regions, so what about them? So we did the exact same experiment, but we used different salts. So we have magnesium nitrate, so this is a 1-to-1 mixture, and we have magnesium nitrate on the left and magnesium perchlorate on the right. And we see that same shift in the nitrate peak, which we use to determine when deliquescence would occur. And so we took different ratios of perchlorate and nitrate, and we looked at how the perchlorate could influence the water uptake of the nitrate salts in the soil. And so the blue dots, once again, are going to be the deliquescence, and the orange triangles are the efflorescence. And then the lines in between is the average of the experiment. So what we can see is that perchlorate seem to be helping or assisting with the magnesium nitrate water uptake or deliquescence. And so if we look at our overall picture, so this is pure magnesium nitrate, and its deliquescence is at 60% RH. However, if we look at our perchlorate mixtures, we can see that the water uptake seems to be assisted by that, and we see this with the downward facing trend. So we also wanted to look at what effect a less hygroscopic or deliquescent salt would have on that. And so we did a 1-to-1 mixture with sulfate nitrates, and we saw that this did not inhibit the water uptake of nitrate because it's still below the deliquescence relative humidity of magnesium nitrate. So finally, we can answer our last question, which is, could the temperature and relative humidity values lead to nitrate salt deliquescence in the soil? So we took our phase diagram and we took relative humidity and temperature data from these two sites in the Atacama Desert. And both of these sites contain nitrates, perchlorates in the soil composition and also sulfates. So site A, which you see above, was relatively close to the ocean and was therefore warmer and more humid. This was likely a contributor to why the nitrate salts in the soil could maintain a stable liquid brine, which is shown by the dark blue highlights, and a metastable brine, which is the light blue highlights, throughout most of the year. Then if we look at Site B, this was more inland and therefore significantly drier and colder. But despite this, we do have points throughout the year in which the salts could uptake and deliquesce and maintain a metastable place. So, of course, this is very highly variable, and that could be due to the different environmental conditions as well as the different soil compositions, and would need to be further studied. So if you have any questions, comments, concerns, or a job, please stop by my poster, which is number 23. So thank you.